Okay, in this video we're going to talk about Newton's divided difference method for interpolation. What is interpolation? Well, there's a figure down here that shows pretty well what it is. Sometimes you are given a discrete set of data, y as a function of x. For instance, one example, one common variable that is a dependent variable is time. And y could be position. And suppose this is that xy represents the position of a certain object at a certain time. For example, you could have the victim of a wreck floating in the ocean, and you know what their position, and they were sighted at various times. So this would be the first sighting, the second sighting, the third sighting, the fourth sighting. And maybe you would like to know what their position is between these times. That's what's called interpolation. We take a continuous function that passes through the points of observation, but also enables us to estimate where the object was in between the observations. So if I took this as x, then my estimate of the position of the object would be this value of y corresponding to x. Once I find the interpolating function, I evaluate the interpolating function at any x, and I can find an estimate for, well, in this case, its position. So the basic idea of interpolation is find a continuous function that passes through a given set of data points. There are various types of interpolation. In this section, we talk about polynomial interpolation. So our continuous function is a polynomial. Now, of course, there's also various types of polynomials. There are linear polynomials. Linear interpolation means that you interpolate using straight lines. The best linear interpolation using this given data would be to take this straight line here, this straight line here, this straight line here. So that would be called linear interpolation. And for many applications, that's fine. But you can see that these straight lines don't smoothly join the motion that passes through these points. So often we would like to use higher order interpolation. And for 4 points, perhaps we'd like to find the highest order possible. The higher the order, the smoother the curve that passes through the points. Now, you can read this section for yourself. I'm going to jump down to the general formula. Here's an example of linear interpolation between two successive points. Now, I would also like to mention that in the text there are various chapters. There's the Lagrange formula, apart from this Newton's divided difference interpolation. In fact, Lagrange formula gives the very same interpolating polynomial. There's only one interpolating polynomial of degree n-1 through n data points. All right, so let me explain that remark. All right, here he does quadratic interpolation. All right, so this can explain my comment here. I have 3 points here, so my n is equal to 3. And my interpolation is quadratic, so quadratic means that the degree is equal to 2 for 3 data points. Okay. Now, if I had 4 data points, I could have degree equal to 3. So here it gives an example. You can read through this example. All right, so let me get down to this general form. Notice that notice the form of the coefficients. The first coefficient is a functional value. The second coefficient is what he calls a divided difference. And what it is this in some ways looks like the formula for derivative. You take the value of the function at one point, subtract the value of the function at another point, and then subtract the distance between the 2 points. So this is like an approximate derivative. This second coefficient, b2, this is a divided difference of divided differences. Okay. So in fact, this is an approximate second derivative. It's an approximate derivative of derivatives. You may remember Taylor's formula, where you take, you have f of x is equal to f of x0 plus x minus x0 times f prime of x0 plus x minus x0 squared times f double prime. Right? You can notice the similarity between Taylor's formula and this divided difference formula. Here we have a functional value, which is a constant. That's what I have here, my functional value evaluated at x0. Here we have a linear difference multiplied by a derivative. Here we have a linear difference multiplied by an approximate derivative. And here we have the product of two linear terms multiplied by a second derivative. Here we have the product of two linear terms multiplied by an approximate second derivative. So Newton's divided difference is very similar in form to the Taylor formula. And in fact, if you take the differences between the x's and make them smaller and smaller, eventually you will end up with the Taylor formula. Okay. So how do we compute these coefficients in this divided difference polynomial? Well, in the general case, there's a very good figure down below. All right. The polynomial is going to have coefficients b0, b1, b2, all the way up to bn. These coefficients will multiply products of this form, x minus x0, x minus x1, x minus x2, etc. And these coefficients are obtained as the b0 is the function value, b1 is a divided difference, b2 is divided difference of divided differences. And the coefficients are defined iteratively in this way. When I want to find b2, I'm going to take the difference of two divided differences divided by the difference between corresponding x values. All right, so we can see that pattern here. When I want to compute the coefficients of my expansion, notice the coefficients are fx0, fx1, x0, fx2, x1, x0. The coefficients are going to be here. This is his b0 here. This is his b1 here. This is his b2 here. And this is his b3 here. So to compute these four coefficients, I'm going to have to create this large table. And it's a iterative, or I can say recursive, method for computing these f's. This setup is perfect for a spreadsheet. So that's what we're going to do in the next video, is set up the spreadsheet that gives us the divided difference coefficients, and we will plot the interpolating function for a particular set of data.